Right. Next, with that definition of Fourier transform, now let's talk about existence. Before we go into examples, we will talk about existence. Okay. So existence of Fourier transform. Okay, existence of Ctft. So this is similar to that of existence of continuous time Fourier series. So what is that? For a signal x of t, correct? So for a signal x of t to have Fourier transform, for a signal x of t to have Fourier transform, that is Ctft, it has to satisfy what here? It has to satisfy which conditions? Yes, the Dirichlet condition. So satisfy the three Dirichlet conditions. Okay, so Dirichlet conditions. Okay, and what are they? The Dirichlet conditions. So what are they? First one, yes. So if you look at the Fourier series, what did we say? We say that x of, over a period x of t, but for Fourier transform, we will not say that. We just say what? We don't use that phrase over a period. So what is the first condition? Full signal x of t should be absolutely integrable. X of t should be absolutely integrable. Okay, it should be absolutely integrable. So what does it mean? Integral minus infinity to infinity mod x of t dt should be less than infinite. So compare this with Fourier series. There we say over a period t, but here we don't say that. So over a complete t, it has to be absolutely integrable. Okay, and similarly, what is the second condition? Second condition is x of t should be, what is that here? X of t should be, oh, not should be, x of t should have, right? So it should have finite number of maxima and minima, correct? So finite number of maxima and minima, finite number of maxima and minima. Okay, right. And what is the next condition? Third condition would be over x of t should be, or x of t should have, okay, x of t should have finite number of discontinuities. Okay, finite number of discontinuities. Okay, if these three conditions are satisfied, then what do we say? We say that the signal x of t will have Fourier transform. So apart from this, Fourier transform may exist if it satisfies one more condition. So well, again, let me call this equation 3. Okay, because we have used equations there. Okay, or one second. So what is that? Sorry, it should be finite number of, okay. So here we'll write down the equation. Okay, this we called it as 2, and hence we call this fellow as 3 and this fellow as 4, this equation as 5 and this equation as 6. Okay, now let us come back to this one. Okay, absolute integrability, let us call it as the equation 7. Okay, so what is the conditions there? The signal x of t should satisfy the three Dirichlet conditions. What are they? X of t should be absolutely integrable, it should have finite number of maxima and minima, and it should have finite number of discontinuities. Then what do we say? Then we say that the signal x of t will have Fourier transform. So it Fourier or indirectly we say Fourier transform of the signal x of t exists. Okay, Fourier transform of the signal x of t exists. Okay, right. Next, there is one more condition which has to be no, apart from Dirichlet conditions, there is one more condition. So what is that? We write down that as an alternate condition. Okay, an alternate condition for existence of, okay, an alternate condition, okay, an alternate condition for existence, okay, existence of Fourier transform is that What is that? Is that x of t should have finite energy. Okay, x of t should have finite energy. So whichever is useful for us, we will choose either the Dirichlet conditions or this condition. So what is that? X of t should have finite energy. So if a signal x of t has finite energy, still it can have continuous time Fourier transform. Okay, right. So that is important. So here we have two conditions. So what is that? The signal x of, for a Fourier transform to exist, the signal x of t should satisfy the three Dirichlet conditions, or an alternate condition is what? An alternate condition is that the signal x of t should have finite energy. Means what? Integral minus infinity to infinity modulus of x of t whole square dt should be less than infinite. Okay, so we call this equation as 8. Okay, just for reference we'll put equation numbers. Okay, so if the energy of a signal is finite, then definitely its Fourier transform still exists. Okay, right. But as I said before, these are sufficient conditions. Okay, that is important. So these are even the Dirichlet conditions and also this alternate condition, both are what? These are sufficient conditions. Okay, so they are sufficient conditions. Okay, so even if these conditions are not satisfied, some signals can have Fourier transform. But if these conditions are satisfied, then signal will definitely have the Fourier transform. Even if they don't satisfy these conditions, still they may have Fourier transform. So that's what it crudely means by sufficient conditions. Okay, right. Yes, so next let's come back to existence of inverse Fourier transform, right? So same rule applies here. Okay, so existence, so when do a signal have inverse Fourier transform? Correct. So existence of inverse Ctft. Okay, so now because the inverse Fourier transform is similar to that of what? Fourier transform itself. So definitely the Fourier transform should satisfy the Dirichlet conditions. Okay, so when do a signal have inverse Fourier transform here? For a signal or for a function. Okay, for a function x of j omega to have inverse Ctft. Correct. So I'll put an underline here. Okay, so for a function x of j omega to have inverse Ctft, it has to satisfy. Okay, so it has to satisfy again what? 3 Dirichlet conditions. Okay, 3 Dirichlet conditions. Okay, and what are they? Same rule. So first one, what is that? X of j omega should be absolutely integrable. Means what? Integral minus infinity to infinity modulus of x of j omega d omega should be absolutely integrable. Means that integral should be less than infinite. So what is the equation number here? Yes, that one is 8. So we'll write this as 9. Okay, right. And what is the next condition? Oh, second condition, x of t should have finite it's not x of t, right? So we have to talk about x of j omega. So x of j omega should have finite number of maxima and minima. Should have finite number of maxima and minima. Okay, finite number of maxima and minima. And also x of t should have finite number of discontinuities. Okay, no, sorry, I am telling about x of t, actually it is x of j omega. Correct. X of j omega should have finite number of maxima and minima. Okay, finite number of maxima and minima is over. So what is the third condition? Finite number of discontinuities. If these three conditions, okay, they are satisfied, then what do we say? the Fourier transform of the signal or inverse Fourier transform of the function x of j omega exists. Okay, and again alternate conditions also we have to bring in. So what is that? So alternate condition, what is that alternate condition? X of j omega should have, correct, x of j omega, correct. So x of j omega should have finite energy. Okay, x of j omega should have finite energy. So what do I mean by that? Whatever may be the function, how do we define energy? Integral minus infinity to infinity mod x of j omega whole square d omega should be less than infinity, and let us call this as 10. So if the function x of j omega satisfies the three Dirichlet conditions, or it satisfies this alternate condition, which means x of j omega has finite energy, then what do we say? We can find inverse Fourier transform for x of j omega. So indirectly you can find the signal x of t. Okay, so both signal and the Fourier transform, if it satisfies the Dirichlet conditions or alternate condition, then what will happen? X of t can have Fourier transform and x of j omega can have inverse Fourier transform. Okay,